Hello, good morning. Good morning, all of you. Welcome to this series of webinars of INCIT-EV project. INCIT-EV project is a project that will end now in June 2024. And the goal of this webinar series is trying to advance some of the outcomes of the project to you. So in this case, after the first webinar that we have concerning bidirectional charging and smart charging, today we are focused on the decision support system that we have developed in this project that is focused with the mobility planning, with the planning of the charging infrastructure in cities. Let me first briefly introduce the agenda and the panelists of today, and then we'll continue with the slots of the agenda. So let me briefly just introduce myself. I'm Miguel Farfol. I'm a project coordinator at CIRFE, and I'm coordinator of the INCIT-EV project. Today we'll have a presentation of the decision support system developed by Links. So it will be presented by Cristiana Bota, a researcher and leader of the development of the tool in the project. Then we'll have an outlook of the charging and power modules that will be presented by Clement Ness from the University of Ljubljana. And finally, we'll have a live demonstration of how this tool works. This live session will be presented by Maxime Costalonga from Atos, R&D project lead. Finally, we'll have some minutes for questions. So whenever you want, or if you want to wait until that time, you can write in the comment sections and ask any questions or doubts that you may have for this webinar. So in order to not lose any time, let me just briefly introduce INCIT-EV project. As said at the beginning, INCIT-EV started in 2020, so it's been more than 4 years that we have been working in this project. The ultimate goal of this project is to develop a set of innovative technologies that will ease and foster the transition to the electric mobility. In a nutshell, we have 6 use cases that covers different prototype technologies that have been developed in the project, including bidirectional charging and smart charging. Also, we have 3 demonstrators for inductive charging, for static and also dynamic, up to high wave speeds. And we have also high power chargers that are controlled by this DSO in order to improve the quality of the grid and being able to operate these super fast chargers to reduce their impact in the grid. And also we have a charging park and ride facility in Turin that use the existing tramway line to connect the chargers in DC in order to reduce the losses for the transformation stages. This project has more than 32 partners. So we have automotive manufacturers, we have technology centers, we have universities, and we have also cities involved also in the EU mission to achieve climate neutrality. So we have a whole consortium to tackle the multiple objectives and actions we have performed during these 4 years. Let me just present the objectives that we have done. We initially, this project is very focused on the final users. So we had a starting time in which we explore the EV user preferences and expectations. We reached more than 3,500 drivers and users. We have been working on interoperability of wireless charging. We've been working in modules of 30 kilowatts that can be installed in any vehicle. And the 3 demo sites that we have developed are totally interoperable between them. We have also working on B2G at all levels. We have slow power chargers of 3 kilowatts up to chargers of 25 kilowatts, looking also at the business models of these new technologies. And of course, we have developed this decision support system that we'll hear shortly about it. Let me just showcase. This is one of our demonstrators for inductive charging. In this case, is dynamic wireless charging. So we are having a final event in June in Paris, in which this technology will be demonstrated. So if you check this information in the INCIT-EV web page, you can register. At this point, there is very limited attendance, as we are reaching more than 150 people. Therefore, if you are interested not only on the inductive charging, but on all the solutions that we have developed, we'll have the opportunity to have several round tables with experts, and also live demonstration of the wireless charging demonstrators that we have developed in the project. So I won't use any additional time. You can check, of course, our website to have additional information, and also the public deliverables that we have generated. And now I will leave the floor to Cristina Bota, that will start the introduction of the DSS and the technical topic of today's webinar.
Thank you, Miguel. I share the screen. Can you see my screen?
Yes.
Okay, thank you. Let's start. So the DSS is a tool that has been developed by a team of three main entities: Links Foundation, that focus on the development of the backend of the two modules related to the mobility. And then the University of Ljubljana, that worked on the development of the backend of two modules related to charging infrastructure and power power grid. And Atos, that worked on the front end and serving application modules. The DSS is a tool that aims to support cities in planning the charging infrastructure network. He wants to give information about where install new infrastructure, how many new infrastructure do we need to meet the e-mobility demand, and the typology of the infrastructure we need, so the power. The target user is wide, because it can be used by municipalities, by transport energy authorities and agency, by charging point operator, e-mobility provider. So all the entities or agency that needs to understand how to meet the needs of e-mobility in a specific territory, mainly urban territory. The function of the DSS are mainly two. The first one, is supporting the optimal charging points planning in a city, and then to the estimation of the impact on the grid of different scenarios, can be present scenario or future scenarios. These are the main requirements of the tool we developed. It is first a user-friendly and customizable tool. It can be used also by cities that do not have many data and or competencies. It can be used with the minimal user inputs, and it can be applied in all European cities because it is based on official and available data set that are based on European level. And these data are then complemented by collected data during the project. We decided to work using a parking-based approach instead of using a OD matrix approach. That means that we don't need to know how electric vehicles trips in the urban context, but we just need to know where and how long they stay parked in a specific zone of the city. And obviously if they need to charge. The topic related to the charging was faced using a mobile phone approach. So a car recharge whenever they can, where they need, and in the origin and in the destination of the trip. So don't along the trip, but or in the region or in the destination. The DSS is composed by 4 modules. The first one is the user behavioral module that describes the user mobility habits and behavior. The second one is the mobility modules that provides insights related to the impact of the habits of the driver on the city. Then we have the charging infrastructure module that provides information related to the charging station that are present on the network, but that should be installed as new to meet the needs of e-mobility. And this module provides also information about the type and the quantities of the new charging station we need to meet the new needs. And then finally, there is the power module that estimates how the additional charging infrastructure impact on the existing power system. The DSS works in 2 different ways because if the user do not have information about charging infrastructure on the territory and about data related to the power grid, the tool can be provided partial results that are the number of vehicles that need to charge, the total energy required by the mobility, and the total energy required spread over the 24 hours of the day. If the user provide also information about the charging infrastructure and power grid, the DSS works in a complete way. So it provides again the number of vehicles that needs to recharge, then the required grid reinforcement KPIs and the number of new charging points needed to meet the demand. The user behavior and mobility module can be include 4 models. The first one, the car parked model, estimates the number of cars that are parked in the different zones of the city during the day. The second one, the electric mobility model, estimates the percentage of electric vehicles that use the urban territory. The third one estimate where the car prefer to charge. So for instance, at home during the night or during the day at work or in other location. And the fourth one estimate the total energy demand needed from the electric vehicle that use the urban context. To go more in deep with this four model, this is the car park model that needs some inputs. These are inputs that the user must give. This is, for instance, the DSS needs a shapefile of the city that split the city in different zones. That can be, for instance, the district of the city. And it needs also some information about car trips, daily car trips. So the total urban trips, so the trips that stay during the day inside the border of the city, then the total outgoing and incoming trips, and also the average number of trips for each car. There are also some default inputs that are embedded in the DSS, and these are related to main database, European database, the ENAC-POP database that provide information about the population distribution during the day and during the night in the city. And then we use also Corinne that provides information about land cover usage. With this input, the module estimates the number of vehicles parked in each zone of the shapefile during the day and during the night of an average day. The electric mobility model needs as an input the percentage of electric vehicles that use the territory of the city, split in full electric and plug-in. In this case, we have two options because the user can input directly the percentage because maybe he knows, or the second option is to run a model that estimates this percentage. This is a model that has been calibrated using a disk choice experiment that was calibrated with some interview in the 5 countries of the project. And it used some attributes that was selected as the main driver for buying an electric car. These attributes are the car cost, the car range, the energy cost, the presence of incentives for purchasing, and the presence of incentive for the usage of electric vehicle. With this input, the model estimates the percentage of the electric vehicle that use the urban territory. About the charging behavior module, we need some default modules, so these are the input that the user don't have to input directly. And they come from the literature, and this is related to the state of charge for the electric vehicle. So the state of charge that vehicle have when start to charge the vehicle and when they finish to charge the vehicle, and the average daily vehicle kilometer traveled by vehicle for the 3 different kind of trips, so urban, outgoing, incoming, and the average consumption of different segment of electric vehicle, again split between full electric and plug-in. Then the DSS needs also other inputs that in this case, we have two options for these inputs, because the inputs are related to the location of the charging operation. In the first option, the user can choose to provide the percentage of the charging location distribution. So we can say, for instance, I know that the 50% of the car recharge at home during the night, and then we have to provide all the other distribution. Or he can decide to run a model that again was calibrated using a discrete choice model that include some attributes that were considered to be the driver for choosing a specific location of the charging operation. These attributes are the price for charging, the average waiting time at the charging point to start a charging operation, the charging time to reach the 50% of the battery, and the percentage of renewable energy that is provided by charging point. So giving some different level of these attributes, the model provide as an output the charging location distribution of electric vehicle per day and per night. And finally, we have the energy demand model. This model is quite independent because it needs as an input some output that are result from the charge behavior modules, and some default inputs that come from the literature that are related to the distribution of the parking starting time of a vehicle in the different locations, some at home, in the workplace, and in other locations. With this input, the model estimated the total energy request by the e-mobility per zone, per day, and per night, so during all the hour of the day. And this, if the user do not have any information about the charging infrastructure and the power grid, so it can be possible to run the other two models of the DSS. This is the final output. If the user has also information about the charging infrastructure and power grid, these output become inputs for charging infrastructure and power modules. I leave now the floor to Clement Knetz of the University of Ljubljana.
Hello, everyone. I hope you can hear me. Thank you, Christiana, for the presentation. So, as Christiana and Maria says, Leopold and I are coming from the University of Ljubljana, and we were in charge for the deployment for the charging infrastructure module and the power module. So you can see on this slide, this is the fifth and sixth step. So basically if we summarize in one or two sentences, based on the user behavior and mobility module, we can estimate what will be the need for the charging on that premises. Then we can estimate the charging infrastructure that will be needed to satisfy the user needs. And based on the new charging infrastructure, then we can estimate what will happen to the grid. So if the grid will need any grid reinforcements to allow every charging infrastructure to be deployed in the grid. If we go to the next slide, Christiana, please. So the first one is the charging infrastructure model. As I said, the results or the model is based on the outputs from the previous two models. The user needs to select or needs to see what is the existing charging infrastructure in the zones. He can do that easily with the open charging map, since it's quite accurate and it's free for every city, basically on the world and in Europe. And then by default, we have another set of inputs. So based on the determination that was made in the working package 9, we have 3 groups of the chargers. So the first one are the slow chargers or slow charging stations. There, the user can use the charging points which have less than 7 kilowatts of power. Then we have the second group. We named it the fast AC charging group. This is between 7 and 22 kilowatts, so the user can, or the owner of the electric vehicle can charge at these points anything between 7 and 22 kilowatts. And of course, we have then the fast charging stations, which the output power of the charging points is set to be more than 22 kilowatts. As I said, by default, we get total energy requested per zone. So this is, we know for every electric vehicle, the amount of electricity that the vehicle wants to consume, so the amount of energy that will be charged, and we also know the day and the starting time slot. We also know what will be the duration. So based on that, then we can calculate in which group he will fall. So we determine that if the user, the owner, will be in the zone less than 4 hours, then he will use the fast charging station. If the owner will be in the zone, or if the vehicle will be parked in the zone anything between 4 and 16 hours, then he will use the fast AC charging station. So he will charge with the charger that has output of 7 to 22 kilowatts. And the last group are the vehicles that will be in the zone for more than 16 hours, so they will use the slow charging station. That was our assumption and also the recommendations, since we do not want to disturb electric grid too much, because then we can get some violations. So in the reality, we also made an assumption that if the user will be in the zone for more than, let's say, 15 hours, he won't use fast charging stations, since the price will be a lot higher, and also because there will be regulation from the grid. What are the outputs? So the outputs are what is the charging point relative use throughout the whole day, and also the use between 6 a.m. to the 10 p.m. Why this time slot? Because basically, if you look at the map and the outputs, you will see that the more than 19% of every trips and parking times are made between that time slot. And here we can see that the charging infrastructure is basically a lot more utilized than throughout the whole day. Then we also know what is the charging point ratio per vehicle, and what is the number of existing and new charging points, not the charging stations. The last step then from our side was to develop the power module. So the power module consists of database, which are default inputs, and the user inputs. Here we had quite a lot of problems. Why? Because of the data. Maybe in Slovenia, this is maybe a little bit special use case. We are in luck, and we have quite good observability of the grid. The data is available, but working with other use case cities, we found out that that's not the case throughout the whole Europe. So we really needed to, let's say, step down our needs from the user side for the inputs, so that basically now we just need, let's say, need two inputs. The first one is the transformer nominal power. So this is the, like the name says, this transformer nominal power of the grid in the zone, and what is the maximum loading of the transformer. Why do we need that? Because we decided at the start of the project that this is not a simulation tool. So we prepared everything with simulations before using this decision support system, and we made simulations as a, let's say, we stored the results from the simulation in the database. We made that on the reference models of the Slovenian grids, where we deployed all the grids into the three different groups. So we had the city groups and the suburban groups and the country group. And then based on these reference models, we can say that this reference grids represents the whole, every, let's say, every grid that goes into the city group. In this way, we managed to escape the need for the simulations and also speed up the process. The optional inputs which can user put in the DSS are the user power demand profile. So if the user knows what are the exact power demand profile, this will also help the accuracy of this power model, which I need maybe to say that this is just an estimation, because we do not have the exact grid. We cannot then get the exact results, but we get a good estimation. And the user also can see the effect of the solar power plants that are installed in the city. Stiana, if you just click. Thank you. So as I said, the inputs from the user behavior and the mobility module are the vehicle parking metrics. So here now we know what is time slot that vehicles are in the zone, and we also know, based on the charging infrastructure model, we know what will be the power impact of the new charging infrastructure. If we go one click further, we come to the outputs. Here we have some power demand model KPIs. We know we can determine, based on the new charging infrastructure, what is the impact. So for how much the power demand will increase. We also know, or can estimate, what will be the power and voltage violations in this zone, because based on the reference models, we know what is the behavior of the grid if you, let's say, have demand 10% more than before installing the charging infrastructure. We also then suggest the user in which zone, if you want, let's say, to have 10 new fast charging stations points and let's say 10 slow charging points, then maybe you will need to reinforce the grid, because the grid itself in this type cannot absorb this impact from the newly deployed charging infrastructure. And we also can estimate what will be the daily energy consumption. And now I will give the floor to Maxime, I think, if I remember correctly.
Yes.
And that's all from our side. Thank you.
Okay, can everyone hear me?
Yes.
Okay, perfect. Okay, perfect. So then let me share screen and proceed to a live demo of the tool. So first, thanks Christiana, and thanks Clement for presenting the tool and giving a great introduction about it. So let me share the screen. So far you should see, not very interestingly, just a Firefox tab. Is it the case?
Yes.
Okay, perfect. So this is just to illustrate that an online version of the DSS is available, at the URL that I'm entering right now, dss.incitev.arienergy.eu. But if you would try to access it, you would be blocked. This is normal because it's while we are still developing it, we block the access to the DSS. But I invite everyone that's interested to contact us so we can arrange also a demo for you or an access. So don't hesitate to do that. So now I will proceed like to show a live demo, like what happened if you were to be given access to the tool. Everything starts with like an authenticating page. So if you don't have credentials, you can register as a new user just by clicking here. And in that case, you just have a very simple form to fill, just basically giving a username, an email, and a password. The rest is purely optional. So I already have an account created, so I don't need to go through this step. So basically, I will connect with my account with the credentials I created, and once I'm connected, I land on a page that basically lists the project that are created. Project basically corresponds to what Christiana mentioned in the beginning of her presentation. That corresponds to a geographical area of interest. So let's create one together so to understand better how it works. So when you create a new project, the only thing you're required to give is like a name for your project. So let's call it, for instance, I don't know, like, yeah, just Torino maybe, and then give a name to the city of interest in that case, so terrain in Italy. And then you have to upload the shapefile that Christiana mentioned previously, that basically gives some geographical information about the city. So I will upload one. I have several available here. And so once this shapefile is uploaded, several things appear, and mainly you have like an overview of like how your shapefile chops your city into zones. So you can here confirm that it corresponds to what you had in mind, and also you have two tables appearing. In that table, this is the data that the power modules of the DSS expects, and that it parsed from your shapefile. So of course, like you don't have to remember all those quantity by heart. Even if Clement just explained them to you, you can always over on each of those quantity to get like more information. But in a nutshell, those quantities are, I mean, aside from like some data to identify all of these zones, the number of existing charging station of various types, like the slow one, the fast one, and the fast alternative one, and also the maximum load that your transformer in the zone can support, as well as its nominal power. And finally, the type of zone that we are talking about, whether it's residential or commercial. And here, in any case, you have a small table that summarizes, that gives you an overview if all the values that you provided in your shapefile are valid. In case you did any kind of mistakes, and for instance, inputted an invalid number here or a negative number, for instance, for the station, it will be signaled to you via this table, and so you can correct your shapefile and re-upload it. So it's important to note that if your values, if some values here are missing or are invalid, you won't be able to run a power simulation. You will be able to run only the mobility simulation that Christiana mentioned. And there will be a warning issued on that page for that purpose. So once you're ready, that all your values are valid, that you're okay with like how your shapefile chop your area of interest, you can hit create project. And so you see that the new project that I just created appear here in the list. So the next step now is to create an analysis on top of it. So what are analysis? This is just like simulation you want to run on your area of interest. So basically that's feeding the inputs, for instance, for the mobility module and some extra outputs for the power module that were presented by my two colleagues before in order to enable the simulation to be run on your city and evaluate the grid impact of your electric vehicle car fleet. So when I create a new analysis, I'm given a form to feed all those inputs. So even if this form may look a little long, don't be too afraid with that, because you actually only ever have to fill it once. Once you're done filling your form, I can show that to you, for instance, with this. Once you're done filling at least one, you can reuse the values of your previous analysis to pre-fill that form. And if you exported the results of your simulation, you can also upload them, so the inputs of your simulation can be reused to refill that form. So you only ever have to do that once, actually. And actually, I won't drag the time by filling all those forms. I'll show you that, yeah, I did already a simulation for the year 2023 in the Torino area that I showed. So you see that if I click this pre-filled the form with those data. So just maybe now change the name, and let's suppose that we want to do another simulation. For instance, I will call that forecast 2025. Perfect. And so I will adjust my reference here to 2025. Again, here, as for when you were creating the project, if you have any doubt about what a quantity in that form represents, you can always hover your mouse on the help button, and it will give you more explanation on what that quantity stands for and what's its role in the simulations. So the rest of the input that you have to provide spreads in two categories. So like the user behavior and mobility modules that Christiania presented, and the power and charging infrastructure module that Clément mentioned. So now, if I go into the detail of this, the first thing that you have to feed are information about the trips within your city. So like the total number of trips that you expect, as well as the incoming and outgoing ones. And you can also input here like a number of average daily trips done by your car. So we'll adjust this quantity here, for instance, to 2.5, saying that there's always a little bit more than just your round trip to work during a day. And you can also adjust other more complex parameters, even if some default values are provided. I'm referring, for instance, here to this distribution of the daily travel distance of your car fleet. So you have a default value that's provided, as Christiania mentioned, but you're free to adjust it to your need should you want to do that. Now, the second type of data that you have to provide are like the spread of the electric vehicle type in your electric vehicle car fleet between two categories, the battery electric vehicle and the plug-in ones. So if you already know that share, you can input it directly here. But if you don't and would like to be provided an estimate, then you can go to that autofill question, and you will be asked more questions, especially about those cars, like typically their price, their autonomy. I'll let you discover those quantity. I won't go into the details here, but by pre-filling that form, then you can obtain an estimate of this spread in your EV car fleet. I will just here make an assumption. I'm interested in making a forecast. I will be very optimistic and say that there is like a 5% of each of this type of cars. So I'm just exaggerating things a little bit here. Now, the last thing that you have to provide for the user behavior and mobility modules are like how your charging points are distributed in terms of their utilization. So in terms of like how they are distributed between work and home and between public and private infrastructure. So here as well, if you know that distribution, perfect, you can input it directly. If you don't, you also have we also have a way to model that just based on simple question that you can answer here. So for instance, here, like I can just use the default value this time and show how it works. And you see that if I hit the get distribution, actually the distribution changed depending on the default values that were provided. again, I would encourage you in the future to play with that in case you don't have that data readily available. And finally, so that's basically it for like the user behavior and mobility. And for the charging infrastructure, most of the data that you had to provide were actually stored in your shapefile. So actually, you don't have any heavy lift to do here anymore. You just have to say if you want or not to do the simulation and what time of the week you're interested in, whether it's weekdays or weekend. This affects like the user behavior profile here. So now if I hit my create analysis, you see that a new row appears in my list of analysis that indicates that I have, with that little yellow clock here, that my analysis is currently being done by the server. So it typically takes a couple of minutes. This can be more if you have a very big area of interest with a lot of zones, can be less if you have a very small area of interest. So in any case, to not keep us waiting, I already have one already that's successfully run. And so you see that once it's done, another icon appears here for you to check the results. In case it fails, you can always check the logs and inspect what was the issue. But now let's go here and check the result of my simulation in 2023. So usually here it will take a couple of seconds to fetch the results for the database. And once they appear, so they are distributed over several plots. Like the main one being taking back your how your shapefile chop your city into zones and giving you feedback for each of these zones. So by default, the quantity that is plotted on this map is the number of vehicles that arrived in the zone at the time indicated on top of this interface. So by default here at 8 o'clock. So when you hover the zone, then you can get the quantity of interest updated in the adjacent table. So then you can know like how much vehicle arrived, you can know what are the existing charging stations that you provided in the shapefile, but also what are the new charging stations that are suggested to you by the power module. So of course you can play with that and inspect quickly what are the results of your simulation here. You can obviously change the time of the day if you're interested more at what happens when people come back to work. You can shift that to the evening hours. You're free to do that, and you can click any quantity also on that table to actually have it plotted on your map. So if you're interested to see like how the new charging station suggested by the power module spread across your city, you're free to plot that. There's actually no problem in doing that. So as I mentioned, this is an overlaying behavior, so you can quickly inspect all the area of interest. Now, if you want to just look at one specific area, you can just select it, and this locks the table in place and also those two graphs. So what are those two graphs? Those are also outputs from like the power module. The one on the right is basically the power demand in the zone as a function of the time of the day. So this is represented by the black curve over there. And if it stays in the green area, this means that basically your grid can sustain the power demand by your EV car fleet. If it were to be above the green area, this means that you need to take action on your grid to be able to sustain that load. And on the right, the graph that you can see is basically the occupancy of your charging station as a function of time. So that's also something that Clement mentioned in his presentation. By default, I plot the one only for the slow charging station, but you can add the fast one. The goal here, and let's look at a more busy area for instance, this basically tells you like how much your station are occupied depending on the time of the day in that area that you selected. And so
maybe if I just jump in for 15 seconds.
Sure, go ahead.
Maybe you can see that the proportion here is look like it's almost, let's say, 100% all the time. That's why, because I mean, why? That's because we didn't let's say plan the charging infrastructure on the peak demand of the vehicles, but on the average. So I think it was 50 or 60% of the time. So if there was, let's say, 10 vehicles maximum, but the average was 6, we planned the 6 charging stations, not 10.
Okay, I see. Yeah, thanks for giving more details here, Clement. And yeah, don't hesitate to jump in any time to clarify things. Yeah, I mean, in any case, also we would encourage people to play with the simulation and to see the expected behavior. So for me, that completes like the overall quick overview of the results section. Know that you can export, as I mentioned earlier, your results here as a simple text JSON document, and you can use that, for instance, to feed your new analysis that you want to create, so you don't have to refill the whole form. So yeah, and with this. So you see that now my other simulation has been done. So we can also like just have a quick look here to compare. I'm taking that freedom because we are a bit in advance on our schedule. So let me speed over my time a little bit. So you see in that case, for instance, I exaggerated a bit the proportion of electric vehicle in the total car fleet. And so this will most likely have an impact on the grid. So if I look at a busy area, this time I'm going into the red zone, and I'm like stressing too much the grid here. So yeah, this was just to say again, I encourage people to play this, either to do like realistic simulation or like forecasts of for the future. And I think that's roughly it for me. So I think we can give floor to the questions if you want, and I'm happy to show more of the DSS on request.
Okay. So for the people attending, if you have any specific question of how this tool works, feel free to write it in the chat. I hope that you have the rights to write it on the chat. Maybe in the meantime, I can start with a question. Is there the possibility to see the results of the power impact if you don't have the grid information, and also to be that as aggregated information, or is it only available by zones?
No, you can see the impact of the power if you don't have any data, because then it would just be, let's say, shooting an arrow and see what you got. You cannot get anything if you don't input. It's like the saying in the machine learning, bad inputs, bad output, good input.
Okay, so there is no possibility to see the energy demand, even if not the impact in the grid, but yes.
No,
yes, the energy demand, yes,
okay.
It's possible.
You can actually, if you want, I can take over again so that I can show that. Like for instance, right now I'm creating another project where I purposefully, for instance, pass a shapefile, like for whatever reason. This could be just empty values if you don't have them. But I've put some with like invalid values. So you see, like basically because of this, I won't be able to run like the power modules. The only thing that changes here is that you will have a warning telling you that you cannot run the power simulation, but you can still run the mobility one. In that very precise case, honestly, let's go through that quickly. I think that's a good test. and that's a good way also to show people that we can actually do those things pretty quickly. So I just reuse the simulation that I've done in another project here, and you see that it's just at this time it tells you like the power and charging infrastructure are not available, but you can still create your analysis and run them. So we'll have to wait a little bit here. That won't be long, to be honest, in that precise case. But basically, the idea here is that you will have the results display of the mobility module plus the energy demand per zone, but you won't have the two graphs that I've shown previously. What will be shown to you will just be like how this energy demand spreads across your area of interest. So yeah, you see, I can illustrate that really quickly, and I think we have a raised hand, so we can maybe hopefully take the question here. But yeah, you see, it's just that the results are more depleted. You just have like the vehicles arrive, and also then you can look at the energy demand on a per zone basis.
Okay, understood.
Yes, about the energy, we have two indicators. The total energy demand, assume that, for instance, the vehicle that want to recharge and arrive at 8 o'clock in the morning, assume that they want to recharge all in 1 hour. And then we have the second KPI, the spread energy, in which we spread this total energy along the parking hour of the vehicle, according to the hour the vehicle stay parked.
Okay, quite nice answers to my question. Thank you for that. We have also a question from Renzo Alexander Morales. I have opened your microphone, so you want to...
Thank you. Hello, thank you for the interesting information. I have a question related with how can we get the information of charging station? Because there are many brands and the information is not available for everybody.
You mean you can't get the information about the existing charging stations, or?
Yeah, about because there is an slot where you can see the number of charging station. So how can you know how many charging stations there are in the place?
In this next version of the DSS, we will also try to deploy that the existing charging infrastructure will be automatically absorbed from the, I think, open charging plan. I'm correct, Christina, right?
Yes, open charge map.
Okay.
Yeah, and there you have quite accurate the data about the charging infrastructure in the whole Europe.
Okay. Okay, that's clear. And in another question, you talked about there are some objectives about interoperability. How can I know when I'm gonna see the map if there is a charging station that is compatible with what I want to charge?
If I may jump in, I believe that you have only considered CCS and Type 2 connectors, which are the standards. Therefore, all vehicles should be compatible by that due to the existing European directives that makes this connector standard, I guess.
No, but I'm talking about the method of payment.
Okay. In this case, for the planning, I believe that we have to consider interoperability between different operators. Am I right?
I think so. I ask confirm to Clement, but I think that the interoperability among payment is not included in the model.
Okay, thank you.
Welcome.
Okay, thank you to your questions. I see that Angel Moya also asked about the topic of the grid reinforcements that you already asked, Clemens, that is not only about the power, but also there is about the violations on overloading and voltage. Therefore, even if it's not clear on the green, even if the power demand is on the green graph, violation is might still happen. Another question. Does the tool consider commercial vehicles as vans or trucks? And is it possible in the outputs to compare private versus public charging needs?
So about the comparison between private and public, in this version of the DSS, it is not possible because it works just on the public charging needs. So, but we do not, we know the how many cars prefer to recharge in domestic and private charging points. So maybe in future step we could add also the private consumption. And about the consider commercial vehicles, so we can include them in the input data related to the number of trips that are doing in the urban context. And at the moment, we consider just the average consumption of car. But we can add, we could add another segment for vehicle, including also specifically truck and vans.
For example, increasing the average consumption,
yes,
due to the increment of percentage of more medium and heavy vehicles. This will work. Yeah.
Yes.
Okay. Thank you for the questions and for the answer. We have also one additional question. Can it be used for larger areas than a city? And what's the limitation in the area? Also, I'm not sure I understood if the tool could be used already. If yes, will you share the link here? So let's first clarify about the area of analysis, and then now the testing possibilities.
About the area, I can say that the limitation is related to, we decided to work in an urban context because we do not include the possibility of charging along the trips. So this is the limitation. If we need to use a more wide area that go over the limit of the urban context, we can, but we need to know that there is not included the possibility of recharging during the trips. And the second question, I don't remember.
Yeah, it's about the testing of the DSS. Yeah. If it is possible for external audience or interested people.
Yeah, I'm writing an answer also for this in the chat, so there is like a possibility for people to get notes of this. Yeah, if I may take on this, and feel free to add anything you want, Christiana or Clement. The idea here is that an online version is already available, but so far it's in closed access while we finalize some details. If you're interested anyway to access it, you can just write to me or Christiana so we can basically arrange an access for you at this stage. That's completely possible. But so far we don't want to put it fully in open access. It's on request, and it might be in the future. That way, then we'll let people know for this.
Okay, that's great. Thank you very much for the questions. Absolutely, I believe that this tool for urban planning is quite a nice asset for urban planners, especially for municipalities or charging point operators that want to assess the situation in a city, and also to establish what will happen in the future with the increasing number of EVs in a specific area. If no additional questions, let me conclude just with a reminder of our final event of the project, in which this will be in 1 month. So therefore, we'll have full information about all the results of the project. Let me share just briefly the agenda. It will be a 2 days event. We'll have first day on the 26th. So we'll have roundtables dedicated for the EV users to know what are the conclusions of the needs and expectations that we got in the project. We'll speak also about grid impact, bidirectional charging, and smart charging solutions that we have developed in the project, such as including in more than 200 public stations smart charging algorithms in order to optimize the grid demand by the EVs as a manageable demand. We'll have also another roundtable with the cities involved in the project that will test, that are testing right now the DSS. So we'll have city planners from the cities to know what are their feedback about these conclusions of the DSS. We have also a specific roundtable for the wireless charging. So we have all the partners and the manufacturers involved in the testing of the wireless charging stations and e-roads that we have developed in the project. And also we will assess the recommendations in terms of normative standards and also pricing assessment of the charging technologies that we have developed in the project. At the end of the first day, we'll have a real demonstration of the high-speed charging lane of wireless charging that we have developed in Versailles in Paris. And the second day, during the late morning, we'll have also a test in 25 meters charging road in a road in Paris. So if you want to attend, just complete the formula that we have on the website, and we will be more than welcome to see you in Paris for the final event of the project. That's all. Thank you very much for your attendance. Thank you for the panelists and for all of you for these nice questions. We'll see you in Paris. Thank you very much.
Thank you, everyone.
Thank you all.
Thank you. Bye-bye.
Bye-bye.